Well, for the interest of time, I'm not going to repeat the first little bit. Sorry for those on the recording. I basically was just talking about the discovery of the Higgs in 2012 and how that coincided with one of the breakthrough papers in deep learning. And as for myself, and I think a lot of physicists, when we saw this at first, it was usually kind of couched in terms of cats versus dogs. And it's kind of easy to not take it very seriously as a scientist. But it's kind of also amazing how much the field of deep learning has evolved in the same amount of time since the discovery of the Higgs in 2012. Now, in this talk, I'm going to try to kind of highlight the work of various graduate students that I'm advising or co-advising on the top in physics and on the bottom in data science, and also some of our postdocs. And at this point, the group is kind of evolved such that we have 3 postdocs that are really core members of the ATLAS experiment, and now have 2 postdocs that were previously, phenomenologists or a type of theoretical physicist, and one who was actually I'm sort of advising that's in Canada. Now, in addition to that, in the last few years, I'd say that I've just kind of exploded in terms of number of collaborations that I've been involved in. So these are just some collaborators from some recent works, and it's kind of a mix of computer scientists and mathematicians and physicists and applied mathematicians. And it's been a lot of fun, I'll say. I've enjoyed myself quite a bit. And I'd also like to thank, the National Science Foundation and the Moore Sloan Foundations for funding a lot of this. Okay, so now to get into the start, I want to talk about the LHC a little bit and kind of just give a thumbnail sketch of how an analysis is done. And this will be very high level. But we have a lot of data at the LHC, and the data is very complicated. So the 2 main things that we need to do are select a very small subset, usually of the enormous number. We have like quadrillions of collisions at the LHC. So we need to select a very small subset of those collisions that are going to be relevant for testing some hypothesis, whether it be the Higgs or supersymmetry or something, extra space-time dimensions or something like that. And then we also need to, because the data is so complicated, we need to kind of come up with a good variable, which I'll call a summary statistic, which is going to be powerful, at being able to distinguish the 2 different hypotheses that we're considering. So the first step of this then would be to take the known processes that exist in the standard model, things that we've known about for decades, and basically predict how many of these are going to satisfy this selection requirement, and what is the distribution of this summary statistic S going to look like. And there might be multiple different kinds of processes that do that. So that's kind of the dark purple and the light purple. Those are like, say, 2 different processes, and you kind of stack them on top of each other, and you get a predicted distribution for what you would expect to see for if, say, a lot of times we refer to this as background. If there's only background and there's no new phenomena, like no new particles happening. And of course, we also have to assess the system, quantify the systematic uncertainties in this, because we don't know our detectors perfectly. And that's a very complicated process, and I'm not going to talk about that really more. But this process is like the bulk of the experimental work that's done. And once that is done, and you kind of freeze the selection and this summary statistic definition, then you make predictions. So I just sort of drew the purple, but how do we do it in practice? Well, it starts with quantum field theory. We have the standard model. Here it is on my coffee mug. And we can make a systematic expansion around that. And that's where you start to see things like Feynman diagrams, which basically describe the very high energy collisions. Here you see things like the process producing a Higgs boson that decays, et cetera. But that's not the end of the story. There are other processes that are involved, because if you make things like quarks and gluons, they like to radiate more quarks and gluons. So you get all this extra radiation, and that process is fairly complicated. And then there's some other processes that don't matter so much for this purpose. And then you get physical particles that are stable enough that they can fly, physical distances, macroscopic distances, and run into our detector. And we need to simulate how those particles interact with the detector. And our detectors have, roughly 100 million sensors in them. So that's takes a few minutes to simulate one of these collisions at the LHC. And now that you have a simulated version of what the energy deposits in the detector would look like, you can basically run all of the algorithms, all these event selection and particle identification algorithms, and compute the summary statistic for one of these collisions but on the simulated data. And so you do that many, many, many times, and that's how you build up this distribution for this, this summary statistic. Okay, so it's very first principles, but it's maybe, as you'll see later, it's not like I have an equation for the distribution for the summary statistic. I need to run through the simulation chain. Okay, now in addition to the background, I'm usually, you know, like say I'm searching for a new particle. Oftentimes, if that particle is there, it would just additively, it'd be some new process and we just add on top of the distribution. And so you just get an extra like red bump on top of the purple, you know, background. And that comes from doing the same thing that I just described before, but not for a background process, for some new process like the Higgs boson. Okay, and then we collect the observed data, that's the black dots there. And then we do some statistical test. And in this case, you see that the data are not in agreement with, you know, they prefer the background only to the signal plus background hypothesis. So then we would reject this theory that predicts the red bump. So that's like, you know, it in a nutshell. Okay. And then, of course, once you're done with that, we write a paper, the graduate students graduate, all of this code kind of rots, and it would be very difficult to reproduce or reuse this work, which is, you know, goes without saying, I suppose. So if we talk about the Higgs particle, what would that look like? Well, here's an example of a collision that's a candidate for the Higgs. You see these 4 red lines. Those are particles called muons that are able to travel all the way through the detector. There are 4 of them in this case, is what we expect. So the selection would be like, go through all of the data and find the ones that have 4 muons in them. And then you'd have a small subset of events. And so then what would I use for a summary statistic, right? This is a very complicated collision. There's a lot of data associated to this one collision. So what would you do? Well, you know, you might think a little bit. The first is, you know, E is not really MC squared. You need to remember that there's, that's only true if you're not moving. If you're moving, then there's also a momentum piece. So the, you know, Einstein really said this is the relativistic formula relating energy, the rest mass, and the momentum of a particle. And so, okay, so how is that useful? Well, every, you know, sort of physics student knows that energy and momentum are conserved. So even though I don't get to observe the Higgs because it decays immediately, whatever energy it had before turned into the energy after, which is the energy in these muons that I can observe. And similarly, the momentum of the Higgs before turns into the sum of the momenta of the muons after. So I can take these equations and kind of plug it in here and solve for m, which should be a constant if I'm actually producing a Higgs particle. So if I just use this formula, this is something that I can observe and I can compute. This is the summary statistic that I'll use. And if I'm actually making Higgs bosons, then I should always get essentially the same number up to experimental resolution. And if it's not a Higgs boson, it'll just be some kind of random number. So this is what it looks like. If you don't have the Higgs boson, you get this kind of blue distribution or the small green thing underneath. If you do have a Higgs boson, then you would get a peak. And in this case, the peak is centered around 125 GeV. And also you see, interestingly, that the data likes to peak there as well, right? So this is like basically how it worked for the Higgs. Okay, now you might be asking me like, okay, great, you know, the Higgs is discovered, the LHC found the Higgs, so you know, what have you done for me lately, right? Like what's happening now for the LHC? So this is a list of 5 of what are considered the science drivers that have been selected by essentially the particle physics community, so, you know, some sort of consensus. And basically the message is that, you know, that there's plenty to do. So first of all, once you found the Higgs, there's the standard model Higgs boson, but if there is new physics, it's often will modify the Higgs properties in some way. So you can actually use the Higgs to indirectly look for the signs of new physics, or the Higgs might actually be able to decay directly into some new particles. So you can use the Higgs as essentially a tool for discovery of new phenomena, and we're doing that. The LHC is not very involved in the physics associated with the neutrino mass, but of course we are one of the ways that you can try to look for dark matter. If you actually produce dark matter, it will fly out of the detector and not interacting with the detector and leave a sign of missing momentum in the detector, and that's something that Alan Mintzer works on, something I used to work on more, and our group has generally worked on. So the LHC is relevant here. We're not very involved in dark energy as far as I'm aware. And then of course, we're very involved in just searching for new particles and interactions and things like that. So that's So the LHC is still involved in sort of 3 of these 5 science drivers. Now, one thing that you might say here is that, okay, well, what about the search for new physics? Like, one thing that happens a lot of times is that, okay, someone did this process that I described, and they searched for some particular theory because, you know, Neil wrote me and it was a good idea, and I wrote my experimental colleagues, and I said, Neil Weiner has this great idea, we should look for it. And so we look for it, we write the paper, and then all the code goes away. And then Josh comes to me and says, like, oh, well, actually, I have another theory. You should look for it. But good news, it looks pretty much like the same, you know, it's got the same sort of final state of particles as what Neil's theory looks like. So the event selection should work, but the distribution of the summary statistic is going to be different. So if I had saved all of that analysis pipeline, I could just reuse it, and I could just do the easy part and fill up the green histogram and then test Josh's theory. But in practice, that's usually not actually possible. So way back in 2010, together with a postdoc, Itai Yavin, who was at NYU, we proposed this idea that the experiment should really invest in making like a service where we save these analysis pipelines so that we can reuse them. So a theorist that doesn't have access to the data can basically make a query that will go through a vetted, you know, analysis procedure by the experiments and then come back with an answer. And so we proposed that back in 2010. We called it Recast. But for years, nothing really happened. People basically said, it's too complicated, or, you know, I don't know, there were naysayers essentially. But then a few years ago, I was lucky enough to get a fantastic graduate student named Lucas Heinrich, and he essentially just built the system on his own, and then went through the very patient work of trying to convince our collaborators. And now, as of basically the last year, this has started to become, we start to actually see results this way, and it's starting to move into the mainstream. So here are 2 different papers now that have used this recast framework to try to reinterpret previous searches for some new phenomena. And I think that that's like a really exciting development for the field, and it's the kind of thing that's going to kind of just systematically improve our ability to use the LHC data to test all sorts of theories. So that's pretty exciting. And there's been an encouraging response from the community, and I highlight here Leonora, who's been involved in some of the training aspects, and here you see all these young people at CERN learning how to use the system. So it's really like a kind of almost overnight switch in terms of practice at the LHC, which I'm very excited about. Okay, so now you could ask the question, okay, that's great, but what if the LHC just, you know, maybe there's some new physics out there and there are new particles, but the LHC doesn't have enough energy to produce them. So then what? You know, the procedure that I just described is not going to work because you're not going to actually be producing the particles and see them directly. So, so there, usually the idea is to use something called effective field theory. And the idea here is that if you have new physics, you know, kind of no matter what it might be, which might be at some very high energy, that's this is like an energy axis. So the kinds of things that Massimo and company are thinking about, or, you know, maybe living up here somewhere, then we're not going to be producing those particles at the LHC, but they can modify the physics subtly for what we can actually measure at lower energies. And what's nice is that you can take the standard model Lagrangian, the thing on my coffee cup, the thing that we've tested very well, and that the Higgs kind of completed the standard model, and essentially add additional terms, which are like perturbations, you know, small modifications to the standard model. And what's nice is that this way of, of expanding it is essentially, you know, fairly unique, and has a, you know, as a kind of general purpose way of parameterizing the effects of new physics. And then you can use that to then make very concrete predictions in terms of just some coefficients, these coefficients here that parameterize these operators, which describe the effects of new physics. And you don't really care about what the actual, you know, high energy physics is. You just care about the values of these parameters. So it's very like practical. And you can predict what the distributions would look like, and the experimentalists can essentially try to measure these coefficients or constrain their values. And then the standard model, these would all be 0. So, okay, so that's very likely, you know, the LHC is kind of ramping up this precision program, which is couched in terms of effective field theory to complement the direct searches. Now, the issue with effective field theory is that usually we expect the deviations from the standard model to be very small. Okay, they're very small changes. So it's very subtle changes compared to the predictions of the standard model. And so if we, for instance, were to talk about the Higgs boson and imagine that we, this is there was some new physics that was going on, it would, for instance, modify how the Higgs interacts or couples to the gauge bosons, like the W and Z boson, or how these other particles decay. And the signature of that is not something as simple as like looking for the invariant mass, where I just look for a peak. Because if the new physics is modifying these couplings, what usually happens is it makes a very subtle change to like angular correlations between particles and things like that. And you get a very like subtle change. And so it's it's no longer obvious what's a good summary statistic to take this complicated data and boil it down. So in this picture, it's a little busy. I put some arrows just to kind of identify what's going on. Here's like these 2 red particles we would see in our detector, these 2 blue particles we would see in our detector. This is another kind of diagram that's more like spatial about what's going on. And you see all these angles and things. And here they're plotted. And this is not actually a very relevant example. It's just a convenient one. But it just shows that there's information in all these different angles. And it's not really obvious like how to boil it down into one number. And the other thing is that what I did before, where I basically simulated events and filled a histogram, is not going to work if my data is like 15-dimensional, because I can't fill, I would need a lot of data to fill a 15-dimensional histogram. Okay, that's very, very sparse kind of data structure. Okay, so that's kind of my roughly my motivation of kind of the main topic of the colloquium. And when I went on sabbatical, this is kind of what I was thinking about. We had discovered the Higgs. We had made the first round of measurements. We'd made the first round of things that were kind of like effective field theory, but not exactly. And it was clear that like the way that we were analyzing the data was not well suited to the task. And so I went to think about like, what could we do? And I started trying to abstract the problem a little bit so that it's not just about LHC physics. So let me abstract it a lot. With this little desk toy that I have and some mathematical notation. So the way I'm going to like abstract a lot is think about, okay, what do we do as physicists? Like there's 2 main things we do as physicists. We make predictions, like we have theories. The theories usually have parameters, like whether they're the cosmological constant or the mass of the Higgs boson or, some, coupling constant of your atomic lattice or something like that. You have a theory, it has parameters. If you have an experimental device involved, you might have nuisance parameters like calibration constants for your device and things like that. And we make predictions of what the data X is going to look like, right? So I'm calling the parameters of interest, the things we really care about, theta, nuisance parameters nu, the kind of raw observed data X. And if we produce summary statistics, like I showed you before, I'm going to call them S of X. They're just some function of the data. And our prediction you can think of as basically a probability model, right? It's describing what's the distribution of the data given those parameters. But they often also include, the prediction also often includes things that we can't directly observe. So there might be things that happen on very short distance scales that we are able to predict, but we don't observe. Or for instance, there might be the momentum of a neutrino in the prediction, but I don't observe the neutrino, it just flies out of my detector. So the things that are random variables that are predicted in the theory, but that I don't get to observe, I'm calling latent variables Z. Okay, so my theory I think of in these kind of probabilistic terms, P of X and Z given theta and nu. And now given the observed data or these summary statistics, my job as like an experimentalist is usually to, well, A, collect the data, and then and come up with this model sort of, but then B, to try to invert it and do inference about the parameters of interest. That's like measure the Higgs boson mass. So that's what I would like to be able to do. And so, why, as you'll see that like it's very easy to say, but it can become difficult to do. So here's this desk toy that I have. I'm going to, flip it over. I don't know. So there we go. It gives me a nice distribution at the bottom. And, think for a second, what do you expect, what's your prediction for what this distribution should look like? You see it all the time. And I actually used it when I was teaching an undergraduate course. And I was going to use it as an example for the binomial distribution, because you basically either bounce to the right or to the left. There's, 10 rows. So I have like 10 tries, and the number of times I bounce right is like, as a binomial distribution. However, the width of this distribution is much larger than you would expect from the binomial distribution. And unfortunately, I didn't realize that until about 5 minutes before I was going to teach. And so that was a little bit embarrassing, but okay. And this is the formula for the binomial distribution, where theta is like the probability of bouncing to the right. Okay. And of course, the way that you get this distribution is you add up all the possible ways that you can land in a particular bin. I'm calling the bin that you land in X, and Z is like the path that you took to get there. So you need to integrate over all the paths to land in a bin. And in this case, because it's a binomial, you can just sum them all up analytically using some combinatoric tricks. However, it didn't work. And why didn't it work? So here it is in a slow motion video I took. And if you see up here, look at these balls. They're bouncing around like crazy, right? They're not like hitting and going to the right or the left, right? They're running into each other. They're bouncing back and forth. They skip over 2 or 3 spots. So the distribution is like much more complicated. I have no idea what it is. I certainly don't have an equation to write down for what this distribution is down at the bottom, but I can simulate it. So here's a simulation of that same thing. And it captures a lot of the physics, and I can tune the parameters of this simulation until it starts to actually describe what's going on. Okay, so this is kind of what I want to get at, is that when we get into simulation, we can really model at a much higher fidelity what's going on, and it's not going to be something that's analytically tractable usually. Okay, so if I wanted to think about what is the probability of X given theta, like theta is the parameters of my simulator, it's still given by the same integral formula, but this integral would be involved summing up over all the possible paths to get there. And the number of possible latent trajectories that you have that end in the same observation X grows like combinatorially. So this integral becomes intractable. There's nothing you're going to be doing with a pencil and paper. So this motivates a new class of inference algorithms for what's called likelihood-free inference, which is kind of a terrible name, or sometimes called simulation-based inference, which is a term that I prefer, which only require the ability to generate samples from your simulator in the so-called forward mode. So basically, I can run the simulator, I can produce fake data from it, but now how do I do inference in that setting? And so that's that's kind of like the subject that I'm very interested in these days. And I think that this is like really kind of generally pretty profound, because science is replete with high fidelity simulators. They go from particle physics to what's going on in neuroscience, to modeling epidemics, gravitational lensing, evolution of the universe and cosmology, molecular dynamics, very practical things like fluid simulations for airplanes, imaging black holes. All of these things involve very detailed simulators where have some mechanistic model involved that's very well motivated from the microphysics, but the resulting observations that you get can be very, very complicated, right? And we would like to be able to do inference in these settings. Okay, and so the way that I would kind of try to say it in a somewhat abstracted way is that, many areas of science have these well-motivated mechanistic models, but the aggregate effect of all of these microscopic interactions of the low-level components leads to an intractable inverse problem. And what I'm pretty excited about is it looks like the developments in machine learning have the ability to effectively bridge the microscopic to macroscopic divide and aid in these kinds of inverse problems. And so in particular, what they can do is they can provide some sort of effective statistical model of the kind of macroscopic or emergent phenomena that you're observing, but it's where the distribution of those macroscopic quantities are still tied back to the low-level microscopic reductionist model. And if you can do that, that's especially if you're going to do it in a semi automated way, like that's a pretty big development. So okay, so I'll pause there for just a second. Okay, so now I'm going to kind of switch and just keep going and talk about how this way of framing the problem is actually, not unique. This term likelihood-free inference, I had actually not really heard of it in physics at all, even though our problems fall into this class of problems. But it was used, for instance, a lot, and you see this. There's some workshops that were happening. It says it's They've been developed mainly outside of the radar of the machine learning community, but they're an important tool for a large and diverse segment of the scientific community, including systems and population biology, computational neuroscience, computer vision, healthcare science, and many others. You know, particle physics is not listed there, and particle physics was not really part of this discussion and was not framing their problems in this language until just recently. And there's a pretty well-known paper that talks about how to do it. And this is one such technique, which is often referred to as ABC for approximate Bayesian computation. I'm not going to go through it, but I'll just highlight a couple things from this paper. One is it talks about, you know, when the data D is high dimensional or continuous, you need to introduce some lower dimensional summary statistics. So that's like what I talked about before with my estimate of the Higgs boson mass. And then it says, but if you're, you know, but in practice, it might be hard or impossible to identify sufficient statistics. Those are like the right variables to use. And you might have to resort to some more heuristic approach, which is basically throw your hands up and, you know, do your best, right? So this was kind of before the machine learning revolution. And what's happened now is that people realize that machine learning can help address some of these issues specifically. So in 2017, the International Conference on Machine Learning held a workshop on, you know, they have different jargon. So they talk about things called implicit models. That would be like the simulator. And here you see they talk about how several real world phenomena are better described by simulators. And here's the terminology that do not admit a tractable density. That's the same thing as saying the likelihood function involves this intractable integral. And now I'm happy to see that they say they're used in physics to generate particle simulations of high energy physics processes. So that I think I have some role in the language there. And so they list a few different techniques, but these are all kind of hot topics in machine learning. The top one, generative adversarial networks, maybe you've heard of before. It was covered in the New York Times. These are kind of neural networks that you sort of basically feed in noise, like randomly distributed, like Gaussian distributed noise. It runs through a neural network where the output is in the space of the data that you care about. So in this case, images. And what it does is it tries to learn the distribution of whatever you care about. So in this example, it's trying to learn the distribution of faces. So these images are not like two-dimensional things. They're 3 million dimensional objects, right? There's roughly 1,000 by 1,000 pixels here. And for each pixel, you have 3 colors. So this image is a point in a 3 million dimensional space. And this image is a different point in a 3 million dimensional space. So what they did is they collected a bunch of pictures of celebrities' faces. And those are just a bunch of points in this very high dimensional space. And they used a neural network to try to learn what that distribution looked like. And then once they were done, they sampled from that distribution. And these are the examples they got. And they look very realistic, right? So that's pretty impressive. And so this is clearly some kind of technique that is not restricted to low dimensional data. And you can discuss it in very concrete probabilistic terms, and we can try to take advantage of these kinds of developments for science. So recently, together with a previous postdoc here and a current postdoc, Johan Bremer, we wrote a review in the Proceedings for the National Academy of Science about what we identify as sort of the frontier of simulation-based inference. And these traditional approaches are kind of down here in the bottom left, where the axes are essentially how expensive is it to run your simulator, or how high dimension is the parameter that you're trying to infer, and the vertical axis is essentially how high dimension, excuse me, is like the dimensionality of your data. Okay, and so what machine learning is allowing us to do is to essentially go to work with higher dimensional data. Other kinds of things like active learning, which I won't really talk about today, though I'm working on with Arena, uses something called active learning to essentially use the simulators more efficiently. And something else that I'll talk about today is basically integrating and augmenting the simulators themselves to be able to kind of go in this diagonal direction and be able to use the simulators more efficiently. Okay, so I'm gonna give you just a taste of what this stuff is about and then show you some physics applications and physics results. Okay, so there are roughly a taxonomy of different approaches for simulation-based inference. One of them on the left is basically to use the simulator more efficiently, and I'll talk a little bit about that later. And the other approach is to learn the simulator, say like using neural networks or some kind of machine learning technique where you're basically approximating the simulator, okay? So I'm gonna talk about two approaches in this column first. Okay, so the high level picture that you can have in mind is that I have a simulator over here. It has some parameters that are physically meaningful, like the mass of the Higgs boson or the cosmological constant or whatever, whatever parameter of your theory you care about. And you're going to tell your simulator to run. It will have all sorts of latent variables inside that we would not be able to observe in the real world. And then it will output some fake data that looks like the data that I'm actually going to collect. And then because I can generate a bunch of fake data, I can then use a neural network that will take in the data and the values of the parameters. So that's the input to the neural network. The thing that's not so obvious is that what do I want the neural network to learn? What I would like it to learn is a likelihood function or likelihood ratio that depends on the observed data and the parameters theta. And if I can learn this, which I haven't shown you how to do yet, but if I can learn this, then I can do statistical inference. I can find the best fit value of theta given the data. I can find confidence intervals with proper error bars, and I can do all the kinds of things that like we do with LHC, but I just have this neural network. And this neural network is basically playing the same role that my histogram played before. It's the histogram that I filled before was my proxy for the probability of the data given the parameters, right? And so this approach is also sometimes referred to as amortized because training this neural network might be expensive, but once you're done training it, evaluating the neural network is very fast, so inference is fast. Okay, so one way of doing that is using basically a very kind of simple trick that's probably known well to a lot of physicists, which is just the change of variables formula. So if I have a random variable z and I have a distribution for that variable, and I called it here R of z, that is actually a slide I took from my colleague Tej. So you have a distribution for z, and that could just be, imagine just a multivariate Gaussian, something very simple that you know. And you take that variable z and you run it through a function. Here it's referred to as the inverse of f. So you run through that function and you get an output called phi. Then what is the distribution of phi, right? It's not going to be a Gaussian anymore. It's going to be everything got shifted around. That's what happened with the generative adversarial network. You took random Gaussian noise, you put it through a neural network, and you got out images, and they look like faces. But this is not a generative adversarial network. It's a different type because I'm going to enforce the fact that I want this function to be a bijection. I want it to be invertible. So the dimensionality of z and the dimensionality of phi need to be the same. And this is actually follows some early work by our colleagues at Courant, Esteban Tabak and Eric Van Eyden that we know quite well in our department. And so they actually did some of this early work, and then it's been picked up where these functions, we're now using neural networks to describe these functions. Okay, so for it to work though, you need these functions to be invertible. They need to be, bijections. And you also need the Jacobian factor that tells you how this distribution turns into this distribution. That's the determinant of this Jacobian factor. You need that to be not incredibly expensive to calculate numerically. So one way to do that is to basically say that this big function, this complex big function, is going to be composed of a lot of simple functions. And you also make it so that these simple functions have like a lower triangular Jacobian, so they're very fast to evaluate. That's kind of details. Okay, so you can, and then there are different types of neural network structures that satisfy these requirements, and people are coming up with new ones all the time. And then they give you a very expressive family of probability distribution functions, where the parameters of that distribution function are the parameters of, say, the neural network or whatever these functions are that are changing variables from z to phi. So that's the basic idea. This approach is called normalizing flows, and it allows you to model distributions in very high dimensions, and the distribution still has a tractable, likelihood function. Okay, a different approach uses classifiers, and so here the idea is that imagine I have just two hypotheses, like cats and dogs, or signal and background, or red and blue, and again the setting here is that I can generate examples, so I can generate red dots and blue dots from my simulator, but I don't actually know what the distribution of the red dots and blue dots is. Like I don't have a formula for it. Now, let's just imagine that I did for a second, and I'm going to consider this functional, okay? It's a loss functional. where I'm going to take the expected value of this thing here, under, say, the red as the red dots are H0, and the blue dots are H1. Okay, so if I knew the distribution, this is just an expected value of this term. And so what is S? S, I'm imagining, is some function that I'm going to apply to the data. And ideally, S would give me 1 if it's a blue dot and 0 if it's a red dot. Like if I could come up with a function that would do that, it would classify the red dots and blue dots perfectly. But if these distributions overlap, then that's not going to be possible, right? There's not going to be any function that's not going to occasionally make mistakes. So I need to, kind of quantify the trade-off of what kind of, how bad is it to make a certain kind of mistake. So this loss function is saying, basically, if the data came as a red dot, I would like S to give you 0. So anything that's different than 0, I'm going to square it, and that's the penalty. And if it's a blue dot, I want it to give me 1, and anything different than 1 is the penalty. I'm going to square it, and that's what's going on. So this seems very ad hoc at this point, I agree, but just consider this thing, okay? If you take this function, or functional, and you imagine that you actually do know this distribution, then you can use calculus of variations to find the function S that minimizes this loss functional. And the function S that minimizes this is written here. Okay, it's pretty intuitive, if you think about it, like the different limiting cases make sense. And this function is also one-to-one with the likelihood ratio, which if you ever took any classical statistics, you should know from the Neyman-Pearson lemma is the optimal way to classify the two hypotheses. So this, from first principles is the right answer for classification. And this is a procedure to effectively get there. But it looks like it's still not useful because I don't know these distributions, but I can approximate these integrals by sampling from the distributions. And I can approximate this loss functional with the kind of like Monte Carlo law of large numbers approximation of this thing. So this I can operationalize by just sampling data from in the forward mode. Okay, so now that I do that, now I need to still carry out the trying to find, in the space of all functions, what function S minimizes this. And I'm not going to consider all functions. I'm going to consider like a variational, ansatz, which is a very flexible family of functions. And the family of functions I'm going to consider are neural networks because they have, they're very, very flexible. And so at that point, just, I think for physicists, you should think of machine learning as like applied calculus of variations. Okay, we're just doing like variational principle stuff. You need to come up with a good loss function that targets what you want. And then it comes with a bunch of optimization algorithms that miraculously work even when you're optimizing like a million or billion parameter function, which is like pretty impressive. And understanding why those things work as well as they do is like an active theoretical question, which I'm not going to talk about. Okay, so that is, I kind of talked about these approaches on the right of learning the simulator. I'll say a little bit about the approaches on the left to not learn the simulator, but to essentially use them more effectively. So imagine here's some code. I don't expect you to read it. It's written in a language probably most physicists aren't familiar with. And so what it's doing though is it's randomly placing these green bumpers in this two-dimensional space. And then it's dropping these balls and it's using a physics engine to like roll out the trajectories of where the balls are going to go, and they bounce around, okay? So the program has random number generators in it. So it's sometimes referred to as a probabilistic program. And these 3 executions of the program, you can think as 3 random draws in the space of executions of this program, right? It's a weird space, but it's the kind of spaces that we're working with, right? So this you could think of as the prior distribution in that space, 3 draws from the prior distribution. But let's say I want to condition on something. I would like 20% of the balls to land over here in this bucket on the far right. You could imagine that you run the simulator like, billions of times, and then you just select the runs of the simulator where 20% of the balls land in the bucket on the right, and that would be the posterior distribution. And here are 3 examples from the posterior distribution of this program running, given 20% of the balls land on the right. But that would be very inefficient to do, right? You would have to run the simulator a bunch of times. Most of the times, no balls land on the right, and it's very hard to get them to land on the right. So how do you do that efficiently? So probabilistic programming is a tool that allows you to do that. And basically what you do is you go in and you hijack all the random numbers in the simulator, and you try to force the simulator to give you the desired output. And when you do that, you keep track of how you're biasing the simulator to get a certain output, but you keep track of how much you biased it. And so you can correct for that or account for it. And you can then basically fill tails of distributions effectively and populate those tails and know what kind of probabilities to assign to them. And the way that you do that often uses machine learning to try to basically act like a puppet master to then control the random number choices inside the simulator. And so here's an example where we have a real observation. It's supposed to be energy deposits in a particle physics calorimeter. And then we use this technique to basically make the simulator give us the desired output. We did this in collaboration with people at Oxford and University of Victoria and the Lawrence Berkeley National Lab. And this paper got nominated for Best Paper at Supercomputing 2019, which was kind of cool. But there we go. That's the basic idea. And I'll return to this idea later. And the name is probabilistic programming. Okay. Interestingly, the tools that we developed are now being used for global health issues, because you have simulators that involve, and the random variables are like, did this person get sick or not? Did they die or not? Did they travel or not? Things like that. And they're using the same tool to hijack malaria simulators and COVID simulators. So that's kind of a nice application beyond physics. Okay, now let me switch to some kind of more physics examples. So at this point, I just gave you a taste of how these two broad classes work. So let me put some physics meat on it. So I'll return to this idea of effective field theory, where we would like to try to test these kinds of things. And what we're really after are these coefficients in front of these operators. Those are the parameters theta that I'm trying to measure or infer. So again, it's the same kind of schematic, and this got we wrote this up in a PRL that got highlighted. Here's the team, including Johan and Irina, and so the examples that we considered at first were just an example of Higgs boson production and this so-called vector boson fusion mode. The new physics is modifying this interaction vertex and this interaction vertex. We have all these particles flying out. Each one of them has, 4 components of, 4 momentum, but then there's a mass constraint. So you can talk about the dimensionality of the data. The so-called phase space is 16-dimensional, but we often work with redundant variables. So we actually worked with 42-dimensional data, and we're trying to infer these 2 parameters, which I'm just going to call, those are the parameters like I called theta earlier. Okay, and I'm sorry that I'm basically glossing over the physics motivation here because I have more than I want to get to. So if you do that, you can work in a simplified case where you can still evaluate the likelihood, and we see the true likelihood, which is essentially just the matrix element for the squared for the particle physicists out there, or the fully differential cross section as this axis, and the vertical axis is our estimate of that quantity using these machine learning techniques. And you see they sit tightly along the diagonal, so we're doing a very good job of estimating the true likelihood. And then we can look to see how well can we measure one of these parameters. That's this axis, and the vertical axis here is the log likelihood. So the more narrow this curve is, the more precise our measurement. And the traditional techniques are the yellow dotted line, and these techniques are the red dotted line. And visually, maybe that's not very impressive. And it corresponds to something like 16% improvement in energy reach, which also maybe doesn't sound like that big of a number, but it corresponds to adding 90% more LHC data. Okay, so like making progress in energy reach is tough business, and this is like one of the flagship measurements of LHC. So if you can do something that's like adding 90% more data, then like that's something worth investing in. You can also compare to like other analyses. So for instance, for the particle physicists here, it's WH production where the Higgs decays into Bs. There's a neutrino involved, which makes life a little tougher. The traditional approach is to kind of basically subset the data into different regions of phase space and count how many events you have in those regions of phase space. If you do that, then for two of these parameters, effective field theory parameters, the red dotted line is how well you would constrain them. 0, 0 in the middle is the standard model. Away from 0, 0 is new physics. So you want the ellipse to be as small as possible around 0, 0. And with the techniques that I just described, it goes from the red thing to the blue ellipse. So that is like a very substantial improvement in sensitivity. So that's pretty, that's pretty cool. And this is work that was done by Sally Dawson and my postdoc Johan. But Sally Dawson is very well known for writing the Higgs Hunter's Guide, very well known phenomenologist. Okay, so now I'm going to switch to talking about dark matter. So in this case, this was like my first paper in astrophysics, and it was together with Sid Sharma, who's a postdoc in CCPP, and along again with Johan and Jill, who I'd developed these techniques with, and Jill's student Yuri. And the basic idea here is that you have like a galaxy. The galaxy is surrounded by a halo of dark matter. That halo is not totally not totally smooth. It has clumpy things in it that are called subhalos. And this is the mass distribution of, or the distribution of the mass of those subhalos. And it looks like a power law. And what's interesting is that depending on the mass of the dark matter particle, you will get some kind of cutoff behavior in this distribution of the subhalo masses. So if you could actually measure this subhalo mass distribution, you would have indirectly be saying something about the mass of the dark matter particle. Of course, the problem is you don't get to see the blue subhalos, right? Because it's dark matter. So what are you going to do, right? Well, what you can use is strong gravitational lensing, where this is the galaxy I was talking about before, and it's a halo of dark matter. You have some background galaxy, its light gets bent, and you get one of these, dramatic, strong gravitational lensed images, where this blue thing is the background galaxy that's being distorted by this foreground galaxy. So what's interesting is that there are some future surveys like LSST and Euclid that are coming online that are going to collect a lot of these strong lenses, and we can maybe use them to try to say something. So what we would like to do is basically infer this is the distribution of the mass distribution for the subhalos of dark matter. It's the power law, so it has like some, beta is like how steeply it's falling, and F sub is like the normalization of that quantity. And so we'd like to be able to say constrain these quantities. We're going to put it through a simulator, and it's going to produce these images, which are 64 squared dimensional objects, because they're images. And so we can run in the forward mode. Inside the simulator, I'll show you more about what's inside the simulator, this black box, in a second. But when we're done, we'd like to be able to train this neural network to invert it so that we can give images in and get inference on these parameters over here. Okay, now we need it to scale to be able to work on many images. We need to capture subtle effects, and we also need to deal with large numbers of subhalos and things like that. So if you wanted to literally integrate over all the things that could happen inside the black box, that's going to be tough. Okay, so I'll just go quickly. We had like in terms of, this is what mainly Sid put together, the model for the the lensing galaxy and the background galaxy. We have a bunch of subhalos that we populate by sampling from this subhalo mass distribution. We include a detector model for Euclid that has a simple point spread function, and we include Poisson fluctuations of the photon counts in the data. That's what the simulator includes. We're not interested in the latent space, the actual like locations of the subhalos and their masses. What we're interested in is inferring the parameters of this distribution. Okay. So we did that, and so here you're going to see images come in on the left, and as they come in, you're going to see a posterior distribution for the two parameters that we're trying to constrain, and then this is basically what the mass distribution looks like. It's this same thing but plotted in a different way. So here they come, the images are coming in, and you start to see that as they come in, our posterior starts to concentrate around the star is the true value that was used to create this mock data. So we're able to kind of correctly infer what the parameters of this dark matter mass function look like, subhalo mass function look like. Okay, and now we also have some very preliminary results where we're using the probabilistic programming technique, which doesn't just give us the high-level population parameters, but also allows us to infer like actual things like, where were the subhalos and what were their masses, and how offset was the galaxy from the lensing system and things like that. And here we're using this probabilistic programming technique, and you can see like here's an observed image, and this is the posterior over all the things that can happen in the simulator. So this is like very recent and preliminary work. Okay, now I realize I should have about 4 minutes left. I'm going to try to burn quickly through a couple of quick topics, and then I'll stop. So thus far, and what I've talked about, it's mainly been like, how do we go about doing inference? And I haven't actually talked at all about like the neural networks themselves. I just talked about neural networks as essentially being a very flexible family of functions. However, it makes sense that we would want to imbue our machine learning models with as much physics as possible, so that we don't have to teach them basic physics. It requires less data to train them, and also so we can be like guaranteed that things like energy and momentum are conserved and stuff like that. So our goals are like to be able to inject domain knowledge, which people call inductive bias, into these machine learning models. And also it'd be great if we could extract knowledge from the models. And it'd also be great if we could like incorporate traditional notions of scientific concerns, including things like interpretability into these models. So that's a whole extra, that's a whole different talk, which I'm not really going to go into, but I'll just give you a taste. So a lot of the ideas here about trying to incorporate compositionality, symmetry, causality, and scale separation into the models. And so I'll just highlight some quick work. So Michael Albergo is a student that came to NYU. He's just starting his second year. Right before he came to NYU, he teamed up with Fiala Shanahan at MIT and her graduate student, Tej Kanwar, and they worked on using this normalizing flow-based picture that I talked about to start to think about lattice field theory. And so here in lattice field theory, you have not a 2D image, but a 4D lattice. And instead of just colors on the sites, you have gauge fields and quantum mechanical fields at the locations. And you would like to, and this movie is, because you're scanning through time, is really just one image. It's like one 4-dimensional image. It's one configuration of this lattice. And what you would actually like to understand is not one of them, but the distribution of all of them. And the distribution of them follows the Boltzmann equation, but you use like the action instead of the energy. And you have this very intractable partition function down at the bottom. Okay. Now, if you go about using normalizing flows to model this distribution, it's very high dimensional. I don't know if I said it here. It's something like 10 to the 9, dimensional data for like modern lattice field theory things. So it's very high dimensional data. And if you try to teach a neural network to learn it, if you don't tell it something else, it's going to have problems. And part of what's going on is that if you take the degrees of freedom and you sort of characterize them in terms of what are called pure gauge degrees of freedom, which are not physically meaningful, and gauge invariant degrees of freedom. The pure gauge degrees of freedom, if you go in that direction, the action doesn't change. So the Boltzmann factor doesn't change. So the distribution is totally constant in that direction. But in the gauge invariant physical directions, the distribution is non-trivial. And if you don't include that, a typical neural network doesn't know that, and it's going to be some arbitrary function, and it's going to be very inefficient. And there are a lot more pure gauge degrees of freedom than there are gauge invariant degrees of freedom. So that's tough. So what we've been working on recently is how to incorporate like space-time symmetries and local gauge symmetries into these neural networks. I won't go into how that works. It's pretty complicated, but it does work. And we've been able to now incorporate things like for arbitrary n, the SUN, the Lie group SUN, SU3 is what's used for the strong force. We've been able to figure out how to make these neural networks be equivariant to those gauge transformations. And we've used that and validated those systems on various lattice field theories. We've investigated scenarios where traditional techniques for sampling that distribution would have problems with getting frozen in certain topological phases, but the approach that we're using does not get frozen in those phases. It very efficiently samples these different topological sectors. And this is also, similar things have been done recently, but not for lattice field theory, but using flows to try to describe the very high dimensional distribution for configurations of atoms and molecular dynamics. And there you have, for instance, metastable configurations of different molecules, which are kind of like the analogs of different topological sectors. And it's very difficult to transition from one metastable state to another metastable state by just moving atoms around in small ways. And this normalizing flow-based approach essentially allows you to sample the whole space kind of independently. And so that's pretty exciting. Okay, and the last thing I'll just flash, since I know I'm kind of beyond time, is has to do with jets at the LHC. Jets are they are the most common object that you have at the LHC. Every collision at the LHC has, usually has one or more jets in them. And they're basically a collimated group of particles that kind of originated from like a quark or a gluon usually. And so our physical model for how they originate starts with like a Feynman diagram with quarks and gluons, followed by this parton shower where you're radiating gluons and things, followed by this hadronization process. And the important part is that all of this stuff happens like at the scale of an atomic nucleus. And so this is all latent. We don't get to observe this tree-like branching process. The only thing we get to observe are these physical particles that fly out and hit our detector. And so if we want to describe the distribution for these leaves, we have to integrate and sum over all the things that could happen in here. And that's very tough. So together with Sebastian Macaluso and incoming graduate student Matt Dernovich, we've been working on making neural network architectures that basically reflect this tree-like structure for both classification tasks, but also for trying to do this kind of probabilistic modeling. And one of the difficulties you have here is you need to sum over all these discrete structures. And even if you only have like 11 particles, there are 600 million binary trees. So this grows like a double factorial. So it grows very, very rapidly. So you're not going to just brute force this thing. So you can use the techniques like I was describing above. And this is some work that Matt produced this summer using probabilistic programming to be able to try to condition the simulator to produce jets that had, either less than whatever that is, 7 particles or more than 23 or whatever the number is. And we can control the simulators now to try to populate these tails more efficiently. And with that, I'll conclude. I think that machine learning, has a lot of promise to be able to help us get more out of our simulators. And it provides basically an effective statistical model for the high-level emergent phenomena that's still tied back to the low-level microscopic reductionist model, which is very important. But learning out how to do this, optimally is going to require a lot more work, and figuring out like how to include systematics and being able to inject and extract our physics knowledge and exploit symmetries and things like this is all going to, it's going to take, several more years of work. And also, I think to really harness the full potential of these techniques is going to require integrating some of these ideas with the simulators themselves. So if you write simulators, I think you should be paying attention to this kind of stuff. Thank you. And I'll also mention that we have a workshop at NeurIPS, which is like the big machine learning conference that's dedicated to machine learning for the physical sciences. And the paper date is, due date is October 2nd. And thank you.
Thank you, Kyle, for this very deep and comprehensive overview. Are there any questions?
I know it was a lot. It was a whirlwind tour.
I mean, I have a general question. Probably you already say that it's a mystery, but you have millions of data points in your, and then this machine learning works with a number of samples or examples that is much less than the number of data or even the number of dimensions in your space. So do we have an understanding of why this machine learning algorithms work? Actually,
yeah, no, it's an excellent question. So so that usually goes under the term of generalization. So usually the worry is that if you have as many parameters as you have data points or something like that, that you'll have horrible overfitting, right? You'll just fit exactly through all your data points. But if you ask how well is this going to work on data that you've not seen before, the prediction could be totally erroneous, right? But that's of course what machine learning practitioners worry about all the time. They want to, the typical plot that people do is they train these models, and then they evaluate how well they work on data they've never seen before. And before the deep learning revolution, the main approach was to try to provide theoretical bounds on how well will this model generalize and predictive performance on data it has not seen before. And there's very nice work by Vapnik and Cherveninkas and this like Russian probabilists to try to put upper bounds on that. That's very beautiful. The problem is that those bounds are incredibly weak. And empirically, things where the bounds should be, like models that might not work very well actually work very well. If you can just empirically take new data and ask how well does it generalize. And so there was a big, like with deep learning, part of the switch was, let's, maybe the theoretical bound is like kind of irrelevant, and we should, practically speaking, we're getting very, very good performance. And so then it's turned into this like theoretical question of why is it working as well as it does? And there, actually, there's been a ton of work in the last few years. That's its own colloquium to try to summarize. I'll point to here Linka Zdabrova, who's one of the leaders in that. She's actually a statistical physicist, and what she worked on things like spin glasses and stuff like that have very complicated free energy surfaces and things like that. And that's similar to the loss landscapes in machine learning. And she's bringing those theoretical tools to bear to try to understand the dynamics of these optimization algorithms and why they generalize as well as they do. And there's actually, there's quite a bit of understanding now, but there's still some, there's still some mysteries involved, but there are quite a few very nice results, and many of which come from theoretical physicists, mainly on the statistical physics side, that understand the, why they generalize as well as they do.
Thank you.
I have a sort of related question, which is, let's pretend that there are deeper reasons for which they work, and they just yet to be found out and spelled out. And then—
I'm sorry, I didn't hear part of it. Let's imagine that there are what?
Let's say that there are deeper reasons for why deep learning works, and they get found out by Lenka and others in the
Eric,
next 10 years.
Yes,
Huh?
And Eric, yeah.
Oh, well, yeah, a bunch of people. And then the question would be, so that's obviously in physics when things work, it's because you've done some free energy minimization and you've actually thought about the correct free energy functional with which to describe your system. So there's like deep reasons for why you have predictive power over things. Now here you set yourself other goals, and again, you have predictive power, but you're not really sure why, but you think there could be deep reasons. Is there a reason to think that biology, in the way of optimizing organisms and the way we function and things like this, is there evidence that it's more like machine learning as a statistical framework of making things work, or more in optimizing the laws of physics to our advantage?
Yeah, that's a great question. I mean, I think let's say, well, I mean, on the first part of that, I would say that oftentimes the thing that's like the free energy is, the loss function. And a lot of times you can prove that if you had like an infinite amount of data, the kind of function that minimizes that loss functional is the thing that you want. So like in that sense, it's a well-motivated loss function. But then the way that you parameterize the thing and what the actual surface looks like and how it interacts with the optimization algorithms and those dynamics is very complicated. And so a lot of the mystery is like how they interact and why it still effectively works, not necessarily that the loss functional wasn't motivated. But it is a very good point that when you go to more biological systems, then you're thinking like, well, is a loss function or loss functional the right way of thinking about the problem? Is there like some global objective that everything is trying to achieve? And, maybe, but it seems perhaps a bit artificial to think that, right? I mean, it definitely seems like the physics of biology is probably going to be more local. And there's, of course, long-term evolutionary pressure and all of that. But there was a very nice talk at this NeurIPS conference last year, which I think it was last year, that was one of the keynotes. And it took this more kind of biological type approach where instead of having a global objective that you're trying to optimize, it was a local, there were local interactions. It looked more like agent-based models or some kind of like little thing, and or like genetic algorithms and little, you know, guys interacting with each other, but they still used ideas of gradient descent and things. And they were able to train these kind of systems that have various emergent behavior, and they do all sorts of wild things. And you can interact with them. You can like cut off the tail of a lizard and it'll grow back and stuff like that. So I think there's, and one of the things they pointed to, and I see that Michael Albergo also mentioned GANs, is that GANs already start to break out of that paradigm. This generative, well, I don't have a slide here, but the generative adversarial network is not minimizing a loss function. It's set up as a game between two players, and the Nash equilibrium has some nice properties, but it's not, you're not minimizing a loss function. It's two things interacting, and the equilibrium has properties. And so that's like the simplest example in that direction. So going into a direction where you have lots of things and it looks like you know, more of a, you know, an ecosystem seems really cool to me, but I don't have much more to say than that.
I like that answer a lot. Thank you.
Thank you.
I have a question.
Please.
Yeah. For GANs, I think I read some paper somewhere that says that, so if you want to use GAN like to simulate a process, that it can do better as the actual data you're feeding into, right? So that's like the upper limit of GAN. So sort of like if you want to simulate events using GANs. And
yeah, I think I see where you're going. Was there more? Sorry, I should let you finish.
Yeah. That was so.
Okay,
So
yes.
like, yeah.
There's this very intuitive thing that like you're not going to get out more than you put in, right? So like if you had like a, you know, 100 pictures of faces or something and you train it, it's hard to imagine how it's going to like generate a bunch of faces. You know, it seems like it's just going to memorize the 10 faces you gave it. And it is true that if you think of like the distribution, or like the space of images, and you've got like a few points in it, that the distribution is just going to make peaks around the data examples that you gave it, right? And then if you generate me some new things, it's just going to memorize those faces and give you back more of the same faces. But you could also say the same thing about like, let's say I want to fit a Gaussian distribution and I have 3 data points. You know, I can fit it. It has a mean, it has a standard deviation, but that parametric family of distributions is not describing all possible distributions. It's describing a subset of distributions.
Yeah.
And so based on those 3, you get a nice Gaussian distribution that generates lots of things you've never seen before. And the way that the extra piece that you gave it was the structure of the family of distributions you care about, right? And so that's often referred to as regularization. Sometimes you're not so explicit as a family that looks like Gaussians. You say like, I'm going to have a family of neural networks, but I'm going to regularize it in some way. Like I'm going to include convolutional components in it so that I see like textures that are going to appear everywhere, and you regularize things in some other way. So it's only through regularization that you get out kind of more than you put in from the data side, but we regularize a lot, and a lot of what we need to do as physicists is think about how do we regularize these neural networks in the appropriate way, and that in some sense is like the theme of these ideas, right? I'm going to bake in symmetries and causality and scale separation, so it doesn't have to learn that. That's like part of the model.
Right. Also, another question related to normalizing flow. So, yeah, I was also reading a paper about that, and it seems that in order for it to be bijective, there's some sort of binding process related in the intermediate layer. Is that correct, or?
I'm not sure 100% which ones you're looking at. I mean, I think, you know, there's like a mathematical way of talking about it, which is just that it's a bijective. And then there's this kind of engineering-based way, which is like, what are the little primitive functions that I'm composing together? And certainly, you know, the little primitive functions often have, you know, restricted expressive capabilities, which is another form of inductive bias. And sometimes that's good. It does what you want, and it restricts you to the relevant distributions. And other times, it's too restrictive and doesn't allow you to model the distribution you actually care about. So, so I think that normalizing flows have seen a ton of work in the last few years, and I think there will be more. Some of the work actually takes like the continuous time limit of these small changes, and you actually model the normalizing flow with ordinary differential equations. And so that's nice, because then the way that you actually might do this kind of inductive bias and things would be like the form of the differential equations. And then it actually starts to look a lot like, physics. The physics and machine learning become so intertangled in each other that it doesn't really make any sense to give them one name or the other.
Yeah, okay, yeah. Thank you.
Thank you. Are there any other questions?
I had a question.
Just a second. Sorry, I will make Kyle a host, so he will be a master of his own destiny. And then he can stop the meeting whenever he feels. Okay, now you go. Yes. Okay. Good. Now you're a host. So please ask the question. Whoever asked the question before.
Yeah, I had a quick question.
Mm-hmm. Yes.
It might be slightly unrelated to your using machine learning for fitting, but if you assume the method works, could you use some set of simple trial data to see something complicated? Like, say you had your fluid equations and you want to turn up the Reynolds number so you see like complex turbulent stuff. Like, how could you see absurd results, or could you get the computer to I guess simulate some more complicated things based on simple physics?
Right. Yeah. So that's it's another great question. So I think the answer to that depends a lot on, like, again, these sort of inductive biases. Like if the networks that you're using have kind of too much flexibility, and you train them in some regime where, let's say, you have laminar flow, it's going to describe the data very well, and and the space of possibilities is going to include things that if you try to extrapolate it to like a turbulent regime, many of which are not going to do the right thing, right? So like that extrapolation, especially when you have like weird chaotic behavior and stuff, like there's no particular reason to think it's going to be, right. If you went to the extreme and somehow you had a neural network that was so, you put so much inductive bias on it that it was essentially just restricted to have like Navier-Stokes equations or something, you just essentially coded up Navier-Stokes as a neural network, then it would do the same thing as you would get if you did normal like computational fluid dynamics, right? So so I think a lot of the interesting stuff is, can you work somewhere in the middle? And there has been some work by Rose Yu that's really nice, where they try to take turbulent flow and they try to when you start getting to the point where there's dissipative things that are going on, and like beyond where you can kind of probe in the kind of turbulent cascade, they can use neural networks to essentially probe that physics and then attach it to a numerical simulation to get the kind of subgrid physics incorporated. So that's a pretty exciting direction, I think. And at some point you can have some weird hybrid of all of these things, so there have been some kind of promising successes of neural networks in the context of fluid mechanics, but I only know a little bit about what's been done there. I'm happy to point you to that stuff.
Thank you. Yeah, I send you an email.
Yeah, great.
Thank you. Other questions? Otherwise, let's thank Kyle again for his
excuse me. I'm sorry, I have a question.
Mm-hmm.
So earlier Kyle mentioned about using the deep learning, using the method to apply them to molecular dynamics simulation, and molecular dynamics could they involve like an interaction of like many bodies, and like so it gets like a lot more complicated, like the more objects you add into a system, and like how well would the model like scale like with the complexity of the system, like in such a scenario.
Right. I mean, I think you kind of have to do it to really know, basically. But these systems that Frank No's group is doing some pretty impressive stuff. And so I think that it looks like it's going to scale pretty well. And also, I have oops, did I just unshare my screen? Sorry. I didn't mean to do that. Okay, sorry. Oh, here I am. Sorry, didn't mean to do that. I was going to show you this slide that kind of gets to that. I didn't have enough time to get to this because I already had too much. But in some of these works, there's like, for instance, oh, you can't see that, can you? Can you see this? Hopefully, there are these so-called graph neural networks where we were modeling, like dynamical systems with some number of balls in them, and it was trying to learn basically what the force law is between them. Between the particles and what the dynamics of the system are. And then what's nice is you can then generalize, you can ask it to predict what will happen for a system that has more balls than you've ever seen before. So it is generalizing to new kinds of systems. We worked later to try to do these kinds of dynamical systems where we actually imposed that somewhere in there should be something like a Hamiltonian, and we used symplectic integrators to try to predict the future. But the dynamics of the Lagrangian and the Hamiltonian were learned. And that ends up being able to predict these kinds of systems, quite well. So you just pick one of the balls and you see it like its orbit of one of those balls. And then they have scaled, not with me, but that group has worked, and they've scaled it now to this systems that look like fluids. And look at that, like on the left is ground truth. And the thing on the right is a prediction, which is really like an atomic type of system where you see all these particles moving around. It's predicting what's going to happen when you like take this lump of dirt and drop it, and the thing on the left is like a actual simulator. So that stuff is like pretty impressive. This is not really normalizing flows. It's like graph neural networks, but it does show that these kinds of things can scale pretty well to pretty complicated systems.
Thank you, Kyle.
Okay, thank you. So I will be leaving now, and then Kyle, if he has the patience to answer more questions, he can. And in any case, we should thank him again already now. But please keep asking questions as long as you want, and as long as Kyle is available for. So thank you again. Goodbye.
All right, thank you. I'll hang out for a second or two. Otherwise, you can send me an email. I'm happy to follow up offline. All right, well then I'll hang up. Thank you all for coming to my TED Talk. Okay, all right, take care. Bye-bye.
Bye, Kyle. Bye, Kyle.